ಅಲ್ಲಿದೆ. So good morning to all. So in the previous class, we were discussing about the unit 3, wherein we could understand the different communication protocols, onboard and external communication boards, and we almost we done with the three important units. The first, okay. So the first unit was a microcontroller, ARM microcontroller, wherein we went with the basics of what is ARM processor and different special purpose registers. Okay, and the followed by the architecture of ARM processor as well. Then moving to the second unit, it was with respect to instruction set and programming of ARM Cortex M3, wherein it we understood the different instruction set and how to write a simple assembly level language by using the set of instructions. And we moving again like in the third chapter, and embedded system components could able to differentiate different types of the embedded systems like a large scale, small scale, and medium scale embedded systems, and difference between the CISC processor and RISC, Harvard and Princeton architectures, Little Indian, Big Indian, and different types of memories, followed by the sensors, actuators, and different types of communication interface. So this is overall of the subject or the syllabus that what we have discussed till now. So almost 70% of the portion is done, remaining with only 2 units. It is sorry, remaining with 3 units done with 3 units. Yeah, we left with another 20 hours of syllabus approximately. So 30 hours of syllabus is done. We left with another 20 hours of syllabus, and probably unit 4 is required little more time because the subtopics are more in unit 4. Okay, so probably I may engage of around 10 or 11 hours, maybe 1 hour or 2 hour extra here. Probably we, and unit 4 is much simpler. Probably you might have already understood the important terminologies related to operating system in your OS subject already, like the types of operating system and process thread and preemptive tasks. The same thing is going to be repeated here also, but probably it is a little bit oriented towards the real-time operating systems. That's it. In the last chapter, we introduced it with introduction to IoT and applications, wherein we go with very basics. What is the machine to machine, and what you mean by cloud to cloud, and as such. And that's good. We able to complete it in another probably in another 20 hours of class. We could finish your embedded class in a well efficient way. Now today we'll start with the unit 4, that is embedded system design concepts. Okay, uh, there it was embedded system components, unit 3. Here it is embedded system design concepts, which are the concepts that you are supposed to remember, or you should know in order to design any embedded systems. Once again, here also conceptual theory and more of what is that the terminologies that what you are supposed to remember. So once again, the textbook remains same here, but from the textbook it is chapter 3, chapter 4, chapter 5 and 7. So these 5 chapters from Shibu put together called as a unit 4. Okay. So these are the different topics that we deal with: characteristics and qualities of embedded systems. So this itself is a chapter in your KV Shibu, chapter number 3. Okay. And chapter 4 from Shibu, it is operational and non-operational quality attributes. This comes under the chapter 3 itself, that is quality attributes of embedded systems. And chapter 4 from Shibu, it is embedded systems application and domain specific. So how we try to design the embedded systems with respect to domain specific. When we say that domain, you can take any of the domains. Say for example, automotive is one such domain, okay, wherein the need of embedded system is more, and followed by the next chapter in Shibu, that is hardware software co-design and programming modeling. So this is very important. Like here you find with some interesting topics wherein we have a finite state machine to design one telephone booth, where how both hardware and software will co-interact with each other to design one particular model. And for firmware design and development, that's the last topic. Probably these two comes under one chapter and one more chapter. So put together almost 1, 2, 3, 4 chapters gives you one unit. Okay, here. Okay. Now coming to the characteristics of embedded systems. Unlike general purpose computing systems, embedded system possess certain specific characteristics. What are those? And those are some of the very important characteristics of embedded system. The first characteristics of embedded system is application and domain specific. The embedded systems are reactive, the embedded systems are real time, and the embedded system can operate in harsh environments as well. These systems are distributed and small in size, and of course, when you compare the weight of the other systems, is very less in weight. Then about, of course, these are about low power systems. That's what we talk about. Embedded systems have little bit of power consumption. So which means that we try to design a device which could consume less battery. So that's where these are the very important characteristics, and we will discuss one by one about these characteristics in detail. Hello. ಹೌದಾ, okay, ಜಾಯ್ನ್ ಆಗ್ತೀನಿ. So now we'll continue with these three characteristics, and next three we'll cover it in next class. That's it. So application and domain specific. Probably the moment you look into this diagram, you can understand that the application, what is the meaning of the characteristic of an embedded system is, one of the characteristic is they are application and domain specific. What do you mean by this? Yes, of course, the embedded systems are designed to perform a specific designed function. So set of functions are defined, and they will work accordingly. If I write a program to control the air condition, then probably it performs the same thing. If I perform a specific task to clean my clothes, then the operating system or the embedded system will perform the same operations, which means more intendedly to perform the functions whatever you have designed it for. Uh, Certainly it cannot be used for any other purpose, which means that I cannot use the washing machine to cool the air, right? So that's what the intended designing the embedded systems for the intended functions. A major criteria which distinguish between the embedded systems and general computing systems. What is the that particular system? That is nothing but, so here in general purpose system, you can replace your hardware to work in different categories, but here you cannot replace a functionality. So that's the major difference, major criteria, what the embedded systems is designed for. So wherein one cannot replace the embedded control unit of your washing machine with your air conditioner embedded control. So it has to perform throughout the once it is designed, so lifetime it has to perform only that particular operation. That's how the embedded systems are designed. Whereas in general purpose computing system, so it is bound to change that functionality. So that's where the general purpose processor are going to be used. The best example for general purpose computing system is your laptops. Okay, the same thing. If I design a scientific calculator, then I should use it as a scientific calculator itself. I cannot use it as a video game player or remote control as such, right? So that's how the embedded systems are said to be application specific and domain specific. They are application specific and they are domain specific. Application, remember that as a air controller is a application. Domain specific, yes, domain specific, the best example for domain specific is automotive sector. Okay, now coming to the next important topic, what do you mean by real-time systems and reactive systems? What do you mean by real-time and reactive systems? What do you mean by reactive? What do you mean by reactive systems? So I have a embedded system wherein some specific algorithm is written. Okay, now for this algorithm, this algorithm will work based on set of inputs, and based on the set of inputs, the algorithm will decide what should be the output. Then what we call this systems now, the machine is reactive to the set of inputs, right? Say for example, I will be monitoring I want to keep my temperature at room, the room temperature always it is supposed to be 27 to 20, 26 to 27 degrees centigrade itself. So this is what we normally call it as a room temperature. Now if the temperature of outside goes below this, so in based on the sensor input, my algorithm try to control the unit, which is that air conditioner. So the job of the air conditioner is based on the output, based on the input sensor. I try to keep all the time in the range of 26 to 27 degrees centigrade. So if it increases outside world, the temperature increases, say for example 29 degree, 30 degree, then again based upon this algorithm, my output of the system will try to decrease the temperature, and it keeps in the range of 26 to 27. Thus now I call this system as an embedded system as a reactive system. Now coming to the definition of this reactive system. So what is the definition? So embedded systems are in constant interaction with the real world. So I told you, giving an example of temperature sensor through the sensor and user defined input devices. So now user defined input devices is something like algorithm or a program that what you try to write. So which are connected to the input port of the systems. So this is the definition of reactive systems. Once again, any change, so again how it works, any change happening in the real world, and we call that change in the changes is called as an event. So any event that occurs, that particular things are going to be captured by the input devices or maybe automated sensors in the real time, and the control algorithm running inside the reactor once again try to control the output variable to the desired level. So that's what I given the best example of the air conditioner here, right? Now So one more important point about the reactive system is embedded system produces change in the output, the response to the changes in the input. So they are generally referred as reactive systems. What do you mean by this? Output changes based on the or response to the change in the input. So in a one line, so the output of a system changes to the response to the change in input. So that's in such cases we call it as the reactive systems. So this is the best example for system being air conditioning. And another example, to be specific, I can call this ABS, anti-lock braking systems. Right? What happens here? See, the moment wheel is locked, okay, so I will be driving my vehicle, and due to in a panic condition, if there is sudden obstacle is detected, or if any person in came in front of my vehicle, knowingly or unknowingly I apply the brake, and I don't release it. See, after applying the brake, if I don't release it, the wheels will not be in motion. Wheels will going to stuck. So what happens when both the wheels of your two wheeler, or both the all four wheels of your four wheeler get stuck? So probably if there will be a skid, right? So the moment the wheels will stops rotating, what happens to the vehicle? So all four wheels are interconnected, and if they are not rotating, if they start rotating, so automatically the vehicle will be in a with a high speed, so suddenly it starts going for skidding. So in such cases, what happens? The sensor will send this signal to the hardware, so microcontroller, wherein it is nothing but applying the brake is nothing but applying the oil. I am trying to push the oil to individual tires, right? So now what I should do, even if I user apply, even if the driver applied the brake, but the job of the ABS is to release that oil, release the pressure in the oil. What happens if I release the pressure in the oil? So it is nothing but, now due to the pressure, the tires got locked. Now after releasing that pressure in the oil, then once again oil will come back from the wheel, then again wheel starts rotating. So this is how automatically it try to control, and effectively the speed of the vehicle is also reduced. And after some time, so again, since the driver has not released the brake so once again, after some times, once again it will apply the pressure in the oil. Once again they try to hold the wheels, again they will release the oil, again uh, again they will apply the pressure in the oil. So it is nothing but, if you assume that how we try to apply the brake when my vehicle is at very speed, I apply, I release the brake. I apply, I release the brake. I apply, I release the brake. The same intelligence is fed to ABS systems. Now, this is once again I call it as a reactive system. Why? Because based on the sensor input, it tried to sense the pressure of the oil, and vehicles are applied. The vehicles are tried to control by reducing the speed. So this is what the microcontroller does the job here. So this inside the microcontroller, now which algorithm is present? So it is nothing but giving the pressure and releasing the pressure in the oil based on the input device. What is that input device? Applying the brake, right? So this is how this is another good example for the reactive systems. Now this is all about reactive system. What about real-time system? What do you mean by real time? Now coming to that particular point here, so real time. What do you mean by this? A real time system operation means which are time deterministic. So which means the the output will be executed with a known amount of time. So wherein the timing behavior of the system should be deterministic, which means that the system should respond to the request or task in a known amount of time. That is what the meaning here. Okay. So now the real time should not miss any deadlines for the task or operation. The best example is deploying of airbag during or whenever the accident takes place. Okay, based on the intensity of the accident. So what it does? So if the intensity of the accident is huge, okay, now there will be a particular timing is decided in the algorithm within a fraction of seconds. Maybe after accident take place, maybe 1 or 2 milliseconds, 1 or 2 milliseconds. Immediately the even less than the millisecond, I could say, the airbag should deploy. So if then the such system we call it as real-time operation or real-time embedded systems. These are all. The ABS is the best example for airbag system is the best example for Airbag system is a best example for real-time embedded systems where it try to meet the deadlines within the timing and they are time deterministic. Okay, for reactive system, you remember the example of air conditioner because and assume that you are trying to keep your room at room level temperature at 25 to 27 degrees centigrade, and based on the output, based on the real world temperature, it try to monitor the temperature at the room. So that's how you can remember the reactive systems and real time systems, you remember the two important word. One is time deterministic and another one is it has to meet the deadlines. So and best example, you can imagine this picture while writing the points for real-time systems wherein the airbag is the best example, and most of the times these types of real-time applications are required in executing the mission critical applications like your flight or even in the the what is that another important like in launching the rockets to the satellites, in launching the satellite during the satellite launch is one of the very important mission critical examples wherein you need to have a time deterministic approach there and wherein the algorithm has to meet the deadlines. The design of these embedded systems, yes, of course, the another very important point here, it has to check the 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 testing of the device should be in such a way that testing of the device is nothing but testing of your algorithm, the algorithm for worst case scenario. Now it has to be considered and the design of embedded system should be real time. Okay, so considering the worst case scenario, so these are the best examples for real time systems. Okay, now okay, what about harsh the operating system, sorry, real-time embedded systems operates in harsh environment. What do you mean by this? So all the time it is not necessary that all embedded systems should be deployed in a controlled environment itself. Maybe somewhere else I can deploy my embedded systems in an uncontrolled environment also. What do you mean by controlled environment and uncontrolled environment now? So the controlled environment where the temperature variation is not too much. Okay, so for example that air condition that is fitted at your home or office wherein you cannot see the adverse temperatures changes. Okay, now the embedded system should work should be deployed maybe very dust place or with a very high temperature zone, right? So where subject it to very it has to observe the shock and as such. Now the this where I need to implement these types of embedded system. Say for example that the geyser connected to one embedded systems, maybe for a home automation system. If the temperature goes beyond that, once again the system should not crash, right? That's how I need to make an observation and make sure that even in the worst case condition it works. Okay, so this is the best example. Due to the climatical change in the conditions, many a times what happens, the thunder and storming, heavy rainfall, there might be a condition where few of your home appliances may disconnect, right? And the device could the device may not start not working due to the fluctuations in the power supply. And that's where embedded systems should be smart enough to withstand, and they will be acting like it's something like a voltage stabilizer, I can call here. I am trying to make my embedded systems to withstand the power fluctuations in such cases. This is one such example I'm trying to give. That's it. There are many such examples where embedded systems are designed to withstand the worst case conditions, wherein it try to observe the shock absorptions takes place, and that shock observations may be due to the fluctuations of your power supply, or the absorption is due to the component aging also, and sometimes there might be a corrosions in your the embedded system device. So even in such cases it should withstand the all the operating conditions. Then once again it should deliver its at its best. Okay, so it should not so happen like once I implemented this home automation by including one embedded system, every year I go on changing this hardware. That should not the case, right? Every time it has to give me a for a longer duration, right? So that's very important point. Okay, now, three more important points with respect to characteristics of embedded systems. That is, they are distributed and small size and weight. So, what do you mean by these important points here? So, we done with these 3 points. So, what do you mean by distributed? What do you mean by distributed? The term distribution stands, or it means that embedded systems may be a part of large systems. May be a part of large systems. Okay, what do you mean by maybe a part of large systems? So assume that there is a one vending machine which what do you mean by vending machine? Vending machine maybe I insert a card in a airport, and other way you can observe this vending machine. So there will be systematic cabins here. In one of the cabin they will be placing the newspapers and the books, magazines, and another way there might be some chocolates here. Okay, and the other maybe a vending of coffee vending machine also, right? So these are the different systems. Now there will be option 1, option 2, option 3. Based on the input option, it try to distribute the output, right? So now that's where I call this as embedded system, maybe a distributed. So it reads the card, you insert the card, and based on the card it will give the option number 1, option number 2, option number 3, and accordingly the option you choose. Say for example, if you're choosing the uh, 2, then it will ask which are the newspaper. Probably it will be having some India Today magazine, or Times magazine, or Deccan Herald paper. It will ask the whichever the paper that it consists of, and once again you click on either of the option, then it will say that how much quantity that is required, and then you say that quantity number, then followed by it asks to detect the required amount from the your card, debit card or credit card, whatever it may be. Now, same thing is true if you want to have a coffee or a tea from a coffee vending machine. So all these three outputs may be in a single embedded system or not. I can able to design this type of embedded systems or not. Yes, definitely it is possible. And such system, such distribution of different output based upon the inputs. So hence such embedded system I call it as a maybe a part of large system, and it is going to render it is going to render the output according to the input. Okay, so another machine ATM is a one another machine where it is a part of large embedded systems, because in turn this ATMs are getting connected to a bigger servers, because and this server will be monitoring that your amount, your account number, because it's not only one individual account number will be there, so there are n number of people's account number, and n number of people account number may be at the different banks. So once again, now ATM machine is a part of large distributed machines, right? So this is one more example for distributed embedded systems. Okay, now ATM is also one good example of these kinds of systems. Okay, now this is all about very small brief introduction about the distributed embedded systems. Now you should know that embedded system is the characteristics of embedded system is application and domain specific, real time and reactive, and they can operate in harsh environment, and they are distributed in nature. Of course, what do you mean by small size and weight? If you observe that the device maybe uh, um, any of the device that you call this as one of the best example for your embedded system is mobile phones itself. So mobile phones nowadays came very handy in nature. Now, earlier you have a small phones, but of course, which was not having this many capability where you cannot able to connect the internet, or you cannot able to transfer the messages through a photo or video. Now this support was not there. Now you can able to observe that those kind of embedded system appears to be very small and less in weight. The other system earlier you can able to see the TV. Okay, you CRT TV, which were having a big. If I want to take it for the repair, then probably I would able to take one auto or one big vehicle to carry that. Nowadays, even I can able to carry my two wheeler. I can able to carry the TV on my two wheeler itself. A very small in size and very less in weight, and probably the functionality when it compares the earlier days, now the functionality is much more, because our TV has also become a very smart. You can connect your TVs to internet, you can cast your screen from mobile phones to TV. So all these are possible, and that is what the innovations in embedded systems. Very small size, and not only small size, small and beautiful, right? You can able to see the shape of your embedded systems, right? So that is what the another important characteristics of embedded systems. What do you mean by power conserve? Yes, of course. What do you mean, what is the battery backup that you are getting right now? So earlier days, yes, of course, we used to say 2 days of battery backup, but for what purpose? Only calling purpose, and probably send the SMS, right? So only for these two purpose we were using, and that's where we could able to say that 2 days or 3 days. And even the advanced mobile phones will give you not less than the 24 hours, in spite of using almost 2 GB of your days data, right? So and that's what the and using and all the time you will be using the video lectures, or you will be using going to the YouTube videos, or even if you watch 3 hours of movie in your mobile phone, still the battery backup is capable of giving you around not less than the 30 almost 12 hours, right? So that's where still I can say that I for a very good battery backup, and the battery life is also very high when compared to the olden days embedded systems. So that's where one of the very important characteristics of embedded systems are, once again, nowadays embedded systems are ultra low power components are available in the market. Okay, also managing the power is also critical, and the battery life is good. This is what I could able to conclude for these important characteristics of embedded systems. Here where we try to stop this session. In the next class we'll go for next important terminologies like attributes of embedded systems. Okay, so this is also one important topic, attributes of embedded systems, and once again, attributes of embedded systems. It is nothing but a functional requirement and non-functional requirement, I could say. Okay, while functioning, what is the requirement, and while non-functioning, what should be the requirement. Okay, so that's where we call it as operational quality attributes and non-operational quality attribute. So if I cover this particular topic, and once again it is going to complete the one chapter of your one in the unit. Okay, as I said you, almost four chapter, this comparing this and this as a one chapter. If I cover that, one chapter is going to be covered from your textbook. So this is another chapter, and so totally combining four chapters, we kept it as a one unit. Okay, so that is enough for the day.